Welcome back, guys. Looks like the microphone's working. Okay, so I was thinking about it this morning, and so yesterday we did the first transistor amplifier miniPCB with the current, that's up to the current design standard. And I thought, well, instead of doing a bunch of transistor amplifier boards that nobody wants, what if I do one good transistor amplifier board? This is just to start, right? Like at the beginning here. One good transistor amplifier board, 2 or 3 good op-amp boards, or one good op-amp board, one good 555 timer board, one good comparator board, one good should I do filter or oscillator? Yeah, but basically do one board per category before doing 2 boards in any category. I don't know. Okay. So in this, these are all old, so I need to go and move them around again. But previously, you could see this is a non-inverting amplifier with bias control and AC coupled input and DC coupled output. This is an inverting amplifier, feedback capacitor with the bias voltage set by a trim potentiometer. And kind of the same thing without the op-amp buffer in the last one. Yeah. So previously, last year, this is what those are, and already saved the sheet to make, so I could just start replacing this stuff. And before we start picking the circuit, I thought, well, let's, I remembered this from many years ago. Yeah, so this is TI's op-amp handbook. And I don't know if y'all, probably not a lot of people know this, but so right after the introduction. So introduction, the op-amp is a great little device. Its applications are broad. And, simplicity and precision that make us feel good. And then this, computation control instrumentation. Originally, the term, wow, okay guys, I did not know this. Or I didn't remember it. No, I don't think I ever knew this. I don't think anybody ever told me this. Originally, the term operational amplifier was used in the computing field to describe amplifiers that perform various mathematical operations. That's why it's an op-amp. Because of the differentiator, integrator, summing, differencing, because of the operations that they used it for in analog computers. It was found that the application of negative feedback around a high-gain DC amplifier would produce a circuit with a precise gain characteristic that depended only on the feedback used. By the proper selection of feedback components, operational amplifier circuits could be used to add, subtract, average, integrate, and differentiate. Yeah, add, subtract, average. Average, I missed that one. That's the... Doesn't that just mean filter? Like a low-pass filter? Huh. Average. Huh. As practical operational amplifier techniques became more widely known, it was apparent that these feedback techniques could be useful in many control and instrumentation applications. Okay, so basically, without being told, we have computing applications, we have control applications, and we have instrumentation applications. And ta-da. What the operational amplifier can do is limited only by the imagination and ingenuity of the user. With a good working knowledge of their characteristics, the user will be able to exploit more fully the useful properties of optional amplifiers. All right, microphone's still good. The feedback technique. The precision and flexibility of the operational amplifier is a direct result of the use of native feedback. Generally speaking, amplifiers employing feedback will have superior operating characteristics at the sacrifice of gain. With enough feedback, the closed-loop amplifier characteristics become a function of the two feedback elements. In the typical feedback circuit, see figure 1, right? Negative feedback. The feedback elements are two resistors. The precision of the closed-loop gain is set by the ratio of the two resistors and is practically independent of the open-loop amplifier. Thus, amplification to almost any degree of precision can be achieved with ease. To almost any degree of precision. Notation and terminology. Texas Instruments employs the industry standard operational amplifier symbols shown in figure 2. Yeah. Some Opamp symbols also include offset null pins, enable disable pins, output voltage threshold inputs, and other specialized functions. Represents a small number of the many Opamp package options offered by Texas Instruments. Wonder if Mr. Brown drew this. Wonder who drew that. This was hand drawn. So you have EI, input voltage, a ZN resistor, which is very, very high, like hundreds of megs to gigs. And then your output voltage, which EI is EI, and then A is your gain. And then Z out, that's your output impedance. So your output voltage, E out, is going to equal, and see how the polarity of your voltage source here is positive, is on ground. So it's going to be negative A times IE. This is with no load. If you put a load which is equal to Z out, then this voltage gets divided by Z out and the load, which equals Z out, and say would be equal, it would be half of this. E out would be, well, E out would be 1 over 2 times negative A EI. Okay. Yeah, dual supply. Drift stabilizing resistor optional. The ideal op amp, right? No load and no output resistance. Defining the ideal operational amplifier. Gain, input impedance, output impedance, response time, and offset. And that's yeah. So if you're an AI researcher and you're looking for circuits to implement math functions, don't forget the op amp with its ideal characteristics, which have been known for decades. So gain, input impedance, output impedance, response time, offset. Because given a device that is an amplifier that has these ideal characteristics, electrical engineers have been using said device in computing circuits since before you were born. I was born, long time. This right? This guy, who polished this application note together, was reading through something from 1963 and 1966, and that's largely what this document is based on. So yeah. Anyways, the ideal op amp. A summing point restraint. An important byproduct of these properties of the ideal operational amplifier is that the summing point, the inverting input, will conduct no current to the amplifier. This property is to become an important tool for circuit analysis and design, for it gives us an inherent restraint on the circuit, a place to begin analysis. Later on, it will also be known that both the inverting and non-inverting inputs must remain at the same voltage, giving us a second powerful tool for analysis as we progress. into the circuits of the next section. Feedback, voltage follower, feedback resistor, non-inverting amplifier, inverting amplifier, intuitive analysis techniques. Yeah, I see. Yeah, integrator, differentiator, intuitive picture of the differentiator. Wow, I like this, the intuitive picture. I wonder if that goes all the way back to the 60s. I wonder if that is what it's largely based on. Differentiator, the cap before the resistor. Oh. Voltage adding. Do they give me an intuitive of this one? Ah, no more intuition. That was fun. Okay. Difference amplifier. I accidentally reinvented this amplifier in 2013 for a project I was working on. I was like, there's got to be a circuit that I could, I had my formula, and I was trying to build an analog circuit to implement my formula. And, I just rediscovered it. But since I rediscovered it, I numbered them R1, 2, 3, 4, instead of saying, hey, let them be the same, let them be the same. And then for my application, I actually wanted them to be different values. So I calculated different values for each one to implement the transfer function that I needed. Man, that was almost 10 years ago. Wow. Analyzing the differential input amplifier circuit as non-inverting. Yeah. Loss of high frequency response when heavy feedback is used. This is why adding that feedback capacitor lightens the feedback, so you can use larger resistors or heavier feedback components. And not sacrifice your high frequency. It's interesting that they call it heavier. Basic practical circuitry. So voltage follower and the inverter. The reason why this guy is super practical is because one of the inputs connects to ground, which usually you have a very good ground plane. Well, ideally, you have a really good ground plane. So it's easy to connect your signal to that ground plane. And then, well, go ahead and connect that other input to the ground plane too. And then the output is on the ground plane. So it's just nice. Whereas if you do like this guy right here, non-inverting, your input and this input are, like this input point and this input point are separated. This input point, well, that's what your signal is on. So you want small noises here to be available on the output. But if this guy wiggles a little bit for whatever reason, then this guy is going to impede or block or resist that signal getting to that input. So, yeah. So, in other words, this is supposed to be your ground plane, right, which is held very constant. And this is supposed to be your guy that wiggles, but it's just, this is a little, this is more practical in real world. So, yeah, that's just one of the things electrical engineers have been dealing with is the psychological negative sign in front of the inverting amplifier, and the fact that the inverting amplifier is better than the non-inverting in a decent number of real-world applications. Yeah, it's because of the ground plane that you could just put on that pin. So yeah, okay. There may be some that non-inverting is better for when you want to get off of that ground plane. Well, but then your signal wouldn't be with, yeah, okay. So you draw a line orthogonal and you come back to the point where it intersects there. And this is the frequency that it's centered at. So the impedance of your capacitor on the input equals RO. That's the lower frequency limit. I did not know that. Wow, you learn something new every day, huh? It says 40 dB per decade is the angle. Yeah, because one's going up, the other's going down. Yeah. Okay. And they're both at the same slope, so they're going to be separated by 90. Yeah, okay. That's good to know. And when you add this resistor here, it adds this plateau on the top. Oh, cool. Cool. So the parasitic resistance in the CI is what will cause this to dome, or kind of plateau up at the top, so it'll kind of come up and then interesting. But you can put this guy here, and then the parasitic resistance there, which would have taken it up a little bit more, but then you'd have variation piece to piece, where you put this guy in, the tolerance on this is real precise, and then you can precisely hold it. And then the variation due to the parasitic resistance in your capacitor will be combined with that, and it won't affect it as much. Gotcha. Okay, cool. That's cool. I like that. Differentiator with stop. So they call that the stop. And that's the amplitude of the differentiator output. So at high frequencies, XC is negligible, and the circuit operates as an amplifier with resistive feedback. That would be up here, right? No, that would be here. This is the amplifier. This is the frequency. Both techniques will be combined to give even better noise rejection. Maybe combined. Yeah. Yeah. Note that a capacitor in parallel with R would have produced the same results with the significant frequency given by. Differentiator with double stop. That and that. Huh. So without those other parts, it's theoretical. If you add just one, it puts this stop. And then if you put the other, it pulls it back. So one grabs this line and pulls it down this way. Yeah. No. I guess just drops it 45 degrees. And then that pulls it back. Cap there. the integrator. Oh, they put a death cross. Oh well. Happens to the best of us. Hmm. 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 The inverting integrators. Practical integrators. Let's put the reset switch. Drift. Had an idea a couple weeks ago. So by clicking play, you agreed to that this is not a public disclosure. No, I guess this is a public disclosure. No, I want to say that. Oh. Well, okay, I won't disclose the invention, but I'll tell you enough so that if you think about it, you can figure it out yourself. But in camera sensors, right? So like in your phone and in your camera, you have a sensor array, which is an array of photodiodes. And basically on, I haven't designed one myself, but probably 6 or 7 years ago when I was looking into it, what I came across is that, I don't know if this is every camera sensor, but I think it is. It's easy to design with a couple transistors, a functional op amp, and these op amps are really small, so you can fabricate them on the same die as your photodiode sensor array, and then they buffer. They're just buffers, right? So no gain, just straight, just an analog buffer. And that way it buffers it to get from the photodiode, the photodetector, to the analog to digital converter. And the idea was, I bet they're not doing this. I'm trying not to disclose anything, but yeah, I bet they're just straight buffering it. I bet they're not doing anything else in the analog domain before they digitize. And I bet I've got some equations that might be interesting, to take those analog signals and then process them through a little bit more analog processing before moving over to the digital domain, especially for systems that need to have a fast response time. Could probably think of a couple car companies that could use that idea. Oh wait, a double integrator integrates twice with one amplifier? Man, the 60s must have been rough. I can't afford a second op amp. I have to figure out how to get a double integration off of this guy. Here, R1, C1, R1. There's just one C1. And it gets squared. Huh. Wow. Double differentiator. You just take the difference amplifier and you amplify both ends of the, or you you basically differentiate both ends of the signal. This integrates the difference between two signals. AC integrator. augmenting integrator. Man, now I really want to do a analog computing section. Differentiators. With stop. High frequency cutoff, low frequency cutoff. Drift compensating resistor. Voltage sum. Sum and average. So why'd they say average? Is it just when the okay. Average is just when the resistors are the same. Alright. The algebraic average, yeah. Scaling adder, yeah. Direct addition. Weighted average. The differential input amplifier. Oh, there it is. R0123. That's what I discovered on my own. Adder subtractor or floating input combiner. Floating input combiner. Floating input combiner. The differential balanced output amplifier. DC amplifiers. Linear gain control. Wow, this guy had 10 amp drive current. Wow. Hmm. V offset 20 microvolts, 6 millivolts. So it benefits from that. Then the output is that, but the output of the overall is that. Current output 10. Wow. Okay. Wow. Wow. Huh. Yep. Gain control. Inverting gain control. Differential output. Yeah. Okay. Difference amplifier. Yeah. So differential and difference. So this has bugged me my whole life. Are we talking about the differentiator, or are we talking about the difference? Differential, difference. AC amplifiers. Hmm. Hmm. AC preamplifier. It's a gain trim. Yeah, so if this guy goes to maximum 10K plus 2.2K, it parallels to 200, so it's really only 190 something, right? And then if you send it to the minimum, so that 10K looks like a 0, then you have 2.2 parallel to a 200, so it's probably like, 150? So the bottom resistance there goes between 150 ohms to 190 ohms. So that potentiometer is a 10K, and it sweeps 10K, but the circuit that it's in, it only adjusts a couple tens of ohms. And then, of course, you would design your resistors. You'd select them such that your target value is when R4 is set to 50%. So that way you get maximum adjustment range on both sides. Current output devices. Hey, the Wheatstone bridge-ish. Not really. No, it's not. Simple meter amplifier. Linear current meter reads AC input voltage. Does it really now? Current output. Simple meter. Yeah, okay. Trust you. Meter amplifier. Yeah, I'm going to trust you. This is supposed to be what? A voltmeter? These circuits were most likely to drive meters. Like that'd be your meter. And this is your amplifier that's going to drive that meter. That's the trimmer. Oof. Well, we don't do it like that anymore, do we, guys? Simple meter amplifier. Man, that's cool. All that just to get a display, a visual display, or no, a quantified measurement. Oh, okay, cool. So people doing AI research should probably consider circuits like this, so that way they could say, hey, I've got a meter, right? It takes this current flow and it gives you this reading, this value, right, out of this. And then this is a signal right here. I'm like, oh, okay, cool. But how do I get that signal onto my meter, right? This is a voltage signal, and that's a current meter. Like, wow, we could do this circuit right here. You find a device to do basically each of these items, and then arrange them together, and figure out how you can modify the design, control the design. Current injector. I'm thinking about like what's his name? That's into like chemistry, computing. Linear current source. So given a voltage in, you'll get a current out. Is that what that is? Yeah. 1 milliamp per volt, 10 milliamps per volt, 100 milliamps per volt. And those are the resistances that R3 needs to be. R3. Deflection coil driver. Huh. Oscillators and multivibrators. Yeah, feedback and phase and gain at the feedback pin. Wine bridge oscillator. Phase, lead, and lag networks. Lag element. Super big capacitance. It's lag. Capacitance is lag. Inductance is lead. Adjustable lead. Lead, lag. It's supposed to be lag, right? So this guy creates the lead and this creates the lag. time delay. Just butterwords. Dead cross. Hmm. Mm-mm-mm-mm-mm. Hmm. Hmm. They didn't need to put that loop. No death crosses, no loops, please. Thank you. Yeah, see, good job, guys. Yeah. Ooh, twin T. So you put a twin T network in it, and you get this. Hmm. Hmm. Focus on limiting specifications. Hmm. 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 Well, anyways, really good read. And it's what I'm gonna, well, you know, so I'm gonna make a op amp amplifier, And then should probably go down to computing and put some of the summing, adding, differential, computing circuits instead of putting them in the amplifier category, because they're really computing circuits. They're not really amplifying circuits. So yeah. Okay. Okay. All right. Well, that's enough for this video. I'll title the video Reviewing Operational Amplifiers. But yeah. Anyways, hope y'all like that. That'll be a little hour-long video reviewing operational amplifiers. Cool. All right, guys. I'm going to save this recording, post it, and then maybe take a break, and then jump back in and make the next mini PCB for you guys. Cool. All right. Thanks, guys. We'll see y'all soon. Bye.